Okay, so moving on to section 9.3, we're going to take our polar numbers, and they're going to be in complex form. In other words, they're going to be written with a real portion and an imaginary portion. That's what complex numbers are, if you remember them from algebra. We're going to be looking to graph them, and then we're also going to be using them for various calculations. Okay, so beginning with the graphs, very easy. Your numbers that the real portion are plotted along the x-axis while the imaginary portions are plotted on the y-axis. So for instance, if you wanted to draw a picture of the sum of these two complex numbers, you would plot this one first. You would go out 6 and then drop down negative 2i, plot a point right there and draw a ray through it. Then you would plot this point, just like you're plotting a point, like as if this was the x-coordinate and this was the y-coordinate. So out negative 4, down to negative 3i, plot a point and run a ray through it. If you want to draw the ray that represents the sum of these two complex numbers, graphically that would be done by the parallelogram method. So you have these two rays already drawn. You draw a line parallel to this blue ray. You draw a line parallel to that blue ray so that you've closed in the parallelogram, and then the line that goes from the origin out to the opposite vertex represents the sum of these two complex numbers, but in graphical form. And you also see that you are at 2 and you're down at negative 5i, that you could get that same answer if you did the calculation algebraically. 6 plus negative 4 is 2. Negative 2i plus negative 3i is negative 5i. So this is the graphical representation of this answer right here. So you're going to be doing it both ways. Yeah, that's what we call the parallelogram form. And then I've given you another example right here. This one is a little bit smaller, but this represents the complex number positive 1 up 3i, plot the point, draw a ray through it. Then there's another complex number here, 4 plus I. So you would go out 4, up 1i, draw a ray through it. And then if you want to draw the ray that represents the sum of these two complex numbers, you use the parallelogram method. So drawing a line parallel to this blue ray would be this dotted line, and this other dotted line represents the line that is parallel to this blue ray, the one that represents 1 plus 3i. And then you draw from the origin out to the opposite vertex, and that represents where you're hitting right there at the vertex. That represents the sum of the original two complex numbers. Okay, this is a graphical picture of the answer. Again, these answers you can get algebraically or graphically. So I wanted to represent that. Again, this is how you can graph some of these things when you want to represent a complex number. And I think I gave you this picture in another section as well. When you represent the x, you're moving out on the positive x-axis. If you go positive yi, you're moving positive y units on the imaginary axis, and that point right there is where you run your vector through. And so the relationships that you were given in the previous sections, if you want to relate your r and your cosine theta to a rectangular coordinate, this would be the relationship. We used this a lot in section 9.1. This has been used in every section in this chapter, and so has the tangent. Although we found that we would always find the reference angle first and then the true theta. So I just reviewed all of these formulas for you from section 9.1, 9.2, and 9.3. Okay, then just some new definitions for you here. The number r is also called the modulus. It's another name for the r value, or the absolute value of a complex number. These are just other phrases that you're going to be seeing with respect to your r value, modulus or absolute value of the complex number. It's actually the distance from the origin out to where the end of the ray is. And then the theta is called the argument of the complex number. Okay, when you get to these problems, finally on page 3, you get to use those formulas. This is the one that is featured in this section where you're finding the trig form of a complex number. So you're going to be starting with a complex number as you would see it in algebra and then taking it to the polar form of a complex number. So it will still have an I portion, it will still have a real portion, but it's going to be in trig form. So it'll have a cosine theta at the front. Your imaginary term will always be attached to your sine value. So if you're going to find this, you're going to find the R value first. And that's all they really ask you for here is the modulus. They're just asking you for R. So that would be R squared is equal to X squared plus Y squared, as we had on the previous page where I summarized those formulas for you. So in this case, it would be negative 24 squared plus negative 7 squared. You're just using the coefficients. Okay, so this is R squared. R is square root of 625, which is 25. So the R value or modulus is 25. Okay, in this one we're writing the complex number in rectangular form. So we are going to take this into the XY system. Now it's still a complex number, so it's going to have a real portion and an imaginary portion. So these are the things we're looking for. We're going for X, we need that, and we also need Y. So X, by the formulas on previous pages, is R times cosine of theta. This is your R value, this is your theta, which appears here as well as here. So it's cosine of theta. Let's put the actual theta in there. That would be 135, and let's roll to 135. I'll put that picture right here, spinning to 135, leaving yourself with a reference angle of 45 degrees. And since that's 45 degrees, this would be square root of 2 over 2, as well as this. Only the horizontal value on the horizontal leg is going to be negative square root of 2. So come back over here. It's 10. Putting in the cosine value, which is the horizontal leg. And this will be negative 10, because you have this negative right here, times square root of 2 over 2. And that'll be negative 5 square root of 2. So I have my X value, and now I need the Y. So I can write the imaginary portion. So Y is R times, let me write the formulas first so you're getting a chance to memorize them by seeing them over and over again. Okay, so the sine value would be this vertical leg, which is square root of 2 over 2, which is 10 square roots of 2 over 2, or just 5 square roots of 2. And then in the end, when you write it as a complex number, but in rectangular form, you still have your real value and then your imaginary value. And Collectively, that's called a complex number, but now it's in rectangular form. Okay, so the whole chapter is a lot of going back and forth between rectangular form and complex form. Okay, moving to number 3. Here you have it in the cis form. This is supposed to be 90 degrees. This is your R value. This is your theta value. So in rectangular form, again, you're going to need an x and a y, because rectangular form of a complex number is when it's written like this. Okay, so finishing this, it would be r times cosine of theta. When we're done with that, we'll go r times sine of theta. Being that this one's at 90 degrees, this should be pretty easy. At 90 degrees, you can't really draw a triangle, but do remember the values. When you rotate to pi over 2, or what's known as 90 degrees, the values right there are 0 and 1. Front number represents the cosine, back number represents the sine. So when you go to do these, this would be x is equal to r times cosine at 90 degrees, which is 24. Cosine is the 0 or just 0. That's your x value. And then the y is the r value again times the sine at 90 degrees, or just 24 times 1. Okay, so when you write it in rectangular complex form, it would be the x value plus your imaginary term. And for it to be an imaginary term, it has to have an I on the end. Or you can just write 24i. It's the same thing as 0 plus 24i. So that would be your final answer. Problem number 4. You're writing the complex number in trig form. Write the complex number in trig form, and you're restated. They give you that formula right there in the directions. You're to stay between 0 and 360, and you're given this point. So if you think about where this point is, you're remember that your real numbers are right here. So 1, 2, 3, 4. You're moving 4 out on the x-axis, and then your imaginary numbers are on the y-axis. So negative 4i would be down here. So out 4, down 4, you're in this quadrant. So when you go to give your r and your theta, you want to be aware of where you're at right here. And you're going to go and look for the x and the y. The r and the theta that goes with this x and y. So r squared is equal to x squared plus y squared. Again, same formulas that you've been using since section 9.1. So we've had a good chance to practice on them. The x is this, and the y is the negative 4. Just using the coefficient. So this is 16 plus 16, that's 32. And then when you want r, it is square root of 32. That breaks down into 16 times 2. This comes out as a 4. So the r value is 4 square root of 2. So I have part of my answer. I'm going to write it in this form when I get done. All I need now is the theta. Okay, so theta you get by the tangent formula. So it's tan of theta. And you're doing the reference angle first. Definition of that is y over x. So that plays the role of the y, the negative 4. The x is the 4. You get a negative 1. And the only way that you can have a tan value of 1 or negative 1 is when the reference angle is 45. Or in other words, pi over 4. I'll help you practice with your pi type answers because those are the type that they most commonly ask for. Although in the directions here, it actually says you can be between 360, which would be an indication that they're going to allow you to answer in degrees. Okay, so this is only the reference angle. Remember that you want to get into this quadrant. So there's two different ways to give that answer. I mean, you could say that you are at 315, because if you're at 315, I mean, if you're in this quadrant right here, and I could draw a better picture over here, just, you know, a little bit more cleaned up. If you're right here and your reference angle is 45 degrees, you could also call that this. You know, your theta is allowed to be any, you got to read these directions, that your theta can be between 0 and 360. Everything between 0 and 360 is a positive angle. That means they don't want you to rotate backwards. So you're going to give some positive answer indicating that you need to rotate this way. So if you rotate all the way almost till you get to 360 but stop 45 degrees before you get there, then that is your real theta. Okay, and this is all understanding that you need to be in quad 4, but with a 45-degree reference angle. And that's how you eventually get the real theta. Okay, so if you're going to write the final answer using the theta, the real theta, and your R value, come up here, and it's R, 4 square roots of 2 times cosine of 315 plus I times the sine of 315. And you now have what was in a rectangular complex number in polar form, or what we call trig form. Polar form and trig form of a complex number are the same thing. Okay, moving to number 5. Now we're looking to find the product in rectangular form as well as the quotient. And both of these are products that are on. This is just in the cis form, and this is in the regular trig form. Okay, so when you're looking, whether it's in the cis form, the compact form, or whether it's in regular trig form, you're basically just multiplying the r's and adding the thetas. So says this formula, that when you want to do a product, right here, multiply the r's, add the thetas. Okay, so in this case it would be 5 times 6, which is 30. And then inside here it would be cosine of 320 plus 130. Use the theta. This is considered theta 1 that you're seeing in the formula. And the thetas that you see over here are considered theta 2. Notice that both of these are the same. They both represent theta 1. Both of these are the same. They represent theta 2. So the formula says that you should be adding theta 1 and theta 2. So 320 plus 130, which is going to be 450, and therefore the other one's going to come out the same. So because it says that for your imaginary portion, which is always with the sine term, that you're going to add theta 1 and theta 2 again, which you see it's going to be 450. So you might as well just write that there. So 30 times cosine of 450 plus I times sine of 450. And why don't we get ourselves back onto the directions and look at where we're supposed to be ending with this problem. This problem says write the product when we've done that, but write it in rectangular form. So you should see no evidence of anything polar or trig-like, because otherwise you haven't gotten all the way to rectangular form. So that means we're going to spin to 450 and go and pick up the rectangular coordinates that are occurring at 450. Okay, so if you went to 450, you'd be going to 360, and then from 360 to get to 450, you'd have to go another 90. That would get you to 450, but that's the same thing as being at 90, and you want the coordinates at that point, which are 0, 1, assuming you're on a unit circle. Okay, remember, the front represents the cosine, back number represents the sine. So to finish this problem and get rid of any evidence of trig terms so that you can go in a rectangular form, cosine of 450 is represented by the 0. And then for your imaginary term, you go and grab the sine at 450, which is the 1. And then you take this 30. It's not degrees. I don't know why I put a degree symbol out there. That's the R value. And you distribute the 30, and you multiply the 30 by the back term. So 30 times 0, 0. And then 30 times this back term is 30i. Final answer, 30i. And there is the product of these two trig complex numbers, but in rectangular form. Likewise, you're going to use the same formula here, even though this is in compact form. This can be rewritten just like this, but you can leave it like this. These would be your R's. That's R1. That's R2. And then your two thetas are pi over 3 and pi over 6. So when you are writing these, you can write them in this form, or you can leave it in this form. You have a cosine term where you're supposed to add the two angles, and you have a sine term, which is your imaginary term in the complex number. And you're adding the same two angles. So one of the angles is pi over 3. The other answer is 5 pi over 6. All right, so now we're going to work to try and get these together. They have different denominators, so this would be multiplied by 2, multiplied by 2, and you have 2 pi over 6 plus 5 pi over 6. And we'll just do the work for this one time because this is going to come out the same anyway. Okay, so for our cosine term and for our sine term, we get 7 pi over 6 with a 21 out front. Again, let's refocus on where we're supposed to be finishing this problem. We're looking for the product. We've done that, but we need to get it in rectangular form. Okay, so you shouldn't have any cosine or sine words in there, so we're going to keep going. The way to get rid of cosine and sine is to actually spin to the designated theta and pick up the x and y values that represent their equivalent. So moving to 7 pi over 6. This would be 6 sixes and then 1 extra 6. That extra 6 represents 30 degrees. So if you're thinking about a triangle, short leg is always across from the 30, which is the reference angle right here. Pi over 6 is 30. So therefore, there's your short leg, but it's negative. This would be the long leg. It is also negative. Don't forget the horizontal leg that runs like this is the cosine. Vertical leg is your sine. So when you come over here now, you're going to plug in for cosine, which is that negative square root of 3 over 2. And then your imaginary term is your sine value, and that would be the negative 1/2. And now distribute. So this would be 21 times square root of 3, oops, left the 1 off, over 2, and there is a negative involved there. I'll put it right out there, just circling it so you can see it. And then it's 21 times 1/2, which is 21 halves. It is negative, and there is an I term. So 21 halves with the I coming off the back. And that's your answer. You are now in rectangular form, and that represents the product. Okay, moving to number 7. You're finding the quotient now, and the only thing that you're going to actually do different here is instead of multiplying the r's like we did for the product, we're going to divide them. And instead of adding the thetas, we're going to subtract them. So in this particular problem, it's 18 divided by 3, which is 6. And then when you go to do the cosine and the sine, which represents your imaginary term, you're going to go the first theta, which is the theta on the top, and this represents the theta, the second theta, the theta that's in the denominator. So it's theta 1 according to this definition minus theta 2. Again, the theta 2 is always in the denominator. And your imaginary portion is going to have the sine with it always, and that same value that you get right in here, which is negative 30 degrees. Let me just write it a little bit better. Just put these in parentheses because they're negative. Okay, so maybe we want to remember about even and odd trig terms. Cosine is an even trig identity, and therefore this negative can be ignored. So this can be written 6 cosine of just 30. Whereas the negative here cannot be ignored because this is an odd trig identity. So you're going to want to take that negative and float it out front, just so you don't have a negative theta. Okay, so now for both of these, you now need a picture at 30, or maybe you remember these values. At 30, your picture looks like this. That means 30 is the central angle. That would make this the short leg. This would represent the long leg, and the hypotenuse would be 1. So when you come over here to finish, again, they want it in rectangular form. So this is 6. Cosine at 30 is represented by the horizontal leg. And the sine at 30 is represented by the vertical leg. This is the sine, and this is always the cosine. So here it's 6 divided by 2, because 6 is the same thing as 6 over 1, so 6 divided by 2 would be 3. Square root of 3 for your front term or real portion of your complex number, and then 1/2 times I for the imaginary portion of your complex number. And that's the complete complex value. Okay, number 8. This is the last one. 16 divided by 8 is 2. And then we're going to go ahead, and in order to complete this quotient, we're going to subtract the theta 1, which is the top theta, and the theta 2. It's always theta 1 minus theta 2, as the formulas say. So get ready to do that. We're going into the complex number now, but we're doing the quotient. We're going into the trig form. So it's cosine of the first theta, the theta in the numerator, minus And then I'll just go ahead and write what this is going to be anyway. 6/5 minus 1/5 is 5/5. I'll just write it like that temporarily, just so you realize that you're talking about 1 pi. So this is 2 times cosine of 1 pi, because 6/5 minus 1/5. And then, of course, the sine is going to have that same theta. Okay, so this is the quotient, but they want it in rectangular form, so you're going to go further by actually spinning to that theta and picking up the cosine and sine value. So when you're at 1 pi, the x-coordinate is -1, y-coordinate is 0. This represents the cosine, this represents the sine. Okay, so continuing with that, cosine is -1. That replaces this entire trig word as well as the theta that's with it. And then the imaginary portion is the sine at pi, which is 0. So this is 2 times -1, -2. 2 times 0i is 0i. Final answer, just -2. And that completes section 9.3.